Section 13.2 is about derivatives and integrals of vector functions. We're going to compute derivatives and integrals of vector functions, and we're going to use them to calculate tangent vectors and tangent lines, much like we use the derivative in ordinary single variable calculus to find the tangent line to the graph of a function. Also, like we did in single variable calculus, we can interpret these derivatives as a velocity or an acceleration. The derivative of a vector function is defined analogously to the derivative of a single variable function. We even use the same notation. For a vector function r of t, we denote the derivative dr dt or r prime of t, and we define it as a limit. The limit as h goes to 0 of r of t plus h minus r of t over h. Notice that we are taking the limit here of a vector function. R of t plus h is a vector, r of t is a vector, and so their difference is also a vector. Dividing by h is like multiplying by 1 over h. That's scalar multiplication. Just like in single variable calculus, we don't want to spend a lot of time stuck on the limit definition of the derivative. Instead, we want to get some sort of formulas that we can actually use. Recall that a vector function can be broken down into component functions. Here I've broken r of t into f of t times I and g of t times j, so f and g are the x and y component functions, and this is just a plane curve. So, how do we compute the derivative, and how is it related to the component functions? Well, let's just follow the definition. The definition says that r prime of t is equal to the limit as h goes to 0 of r of t plus h minus r of t all over h. But we can use the component functions to rewrite r of t. So instead of r of t plus h, we can write that as f of t plus h times I plus g of t plus h times j. And then when we subtract r of t, we can subtract f of t times I, and we can subtract g of t times j. All of this is divided by h. And then I'd like to collect the like terms. I'd like to collect the I terms and the j terms into their own expressions. So I'll factor out an I from f of t plus h minus f of t. Put some brackets around it, put an I there. And then I'll factor out the j from g of t plus h minus g of t. Those are both times j, and all of this is over h. You may see what I'm about to do here. Now that I've got this broken up as into the I and j components, I'm actually going to break the limit into two separate limits. I'm allowed to do this by the sum rules of limits, so long as the sum and limits actually exist. So here are the limits that this would break up into. It would break up into f of t plus h minus f of t over h. I'll put the I out to the side, plus the limit as h goes to 0 of g of t plus h minus g of t over h, and again I'll put the j out to the side. Take a moment and look at this limit and this limit. What are these? Well, these are the ordinary derivatives of the real valued functions f and g. And so this is f prime of t times I plus g prime of t times j. This suggests that if we want to take the derivative of the vector function r, all we need to do is take the derivative of the component functions. The derivative of the function f stays attached to the I vector, the derivative of the function g stays attached to the j vector, and so long as those derivatives exist, we have a derivative of r of t. Here's the result we just derived, written nicely as a theorem. If r of t is equal to f of t times I plus g of t times j, then r prime of t is equal to f prime of t times I plus g prime of t times j, provided those derivatives exist. Similarly, the same reasoning will work for a space curve, where you have an f of t, a g of t, and an h of t as your component functions. You just take the derivative of each component function, and then, provided those derivatives actually exist, you have the derivative of your vector function. Now that we've seen how the derivative is defined, and that in fact it just breaks down into real value derivatives on each component, it should be no surprise to us that some of the same properties and rules that we have for limits of single variable functions also apply to vector functions. So here are a few of them. We have a sum rule, which says that the derivative of the sum of two functions, u and v, is equal to the sum of their derivatives. We have a constant multiple rule, which says that if you take the constant multiple of a function and take its derivative, that's the same as taking the derivative and then multiplying that derivative by that constant. We also have some rules here, though, that are a little more exotic. The third rule here says that if you have a function f, a real valued function, times a vector function u, then you can take the derivative of that using the product rule. And the product rule looks exactly like you'd expect it to be. What's odd here is that we are multiplying a scalar function by a vector function. Of course, if we can multiply scalars by vectors, one might ask what happens with dot products and cross products. And perhaps even more surprisingly, the product rule also works for those. So you can take the derivative of a dot product. Of course, a dot product of u and v is actually just a real valued function. Or you could take a cross product of u and v if u and v are space curves, that is three-dimensional. And either way, the product rule applies. The derivative of a vector function can be thought of as an instantaneous rate of change, but it can also be thought about geometrically. We'll use the following definition. The vector r prime of t is actually called the tangent vector to the curve defined by r of t. If we have some particular point p, which is defined by r of a for some number a, then we call r prime of a the tangent vector at the point p. If for some reason we want our tangent vectors to be 1 unit long, we can construct the unit tangent vector. All we need to do is we take r prime of a, and then we divide by the length of r prime of a, as we have made unit vectors in the past, and we call that capital T of a the unit tangent vector at that point. Finally, we can define a tangent line at p. The tangent line at p is just the line that goes through p and that is parallel to r prime of t. That is, r prime of t becomes the direction vector, and that's what you see here. We plug in the value a that defines the point p, and that gives us our direction vector of our line. Our position vector is just r of a, because r of a defines the point p. And so we're just saying that this is p plus, well, tv, but since t is already used as the parameter for r, we use the parameter s instead to avoid confusion. Now let's find the equation of a tangent line. We'll find the equation of the tangent line to this space curve here, ti plus t squared j plus t cubed k, which we graphed last section. The point, -2, 4, -8, is a point on this curve. So what do we need in order to find the equation of a line? We need a point. Well, we have a point. The point is -2, 4, 8, the point of tangency. We also need a direction vector. The direction vector will be the tangent vector, r prime of t. Of course, we have to figure out what is t. Well, it's not hard to see if we just equate, for instance, this term with this term, we get t equals -2. And so we can compute r prime of t by taking the derivative of each term. The derivative of t is 1, so we'll have 1i. The derivative of t squared is 2t, so we'll have 2tj. The derivative of t cubed is 3t squared k. And if we want the tangent vector at negative 2, we just plug in negative 2. We get I minus 4j plus 12k. This will be our direction vector. So now we can write the equation of our tangent line. Our tangent line we'll call L of s, where s is going to be our parameter just to avoid reusing t, is going to be negative 2, 4, negative 8. That's our position vector, plus s times our direction vector, which is 1, negative 4, 12. And here's a picture. The space curve is given in black, and in the bluish gray is the tangent line whose equation we just calculated. We can also define the definite integral of a vector function, analogously to how it's done for single variable functions. The definite integral from a to b of a vector function r of t is denoted as the integral from a to b of r of t dt, just like for real variable functions. The way it's defined is also identical. We take a subdivision of our domain, so if t starts at a and goes to b, we can divide that up into pieces where each piece has width delta t. And then inside each range, we can find a ti star. So this could be t1 star, could be a point in this range. t2 star could be a point in this range. t3 star could be a point in this range, etc. We then evaluate r at each of those points. And so that evaluation goes here. We multiply the value of the function times delta t, just like we do for single variable functions, and then we add up all of those vectors. This gives us an approximation of the integral. If we want the actual value of the integral, we take the limit as the number of subintervals in our subdivision goes to infinity, so we take smaller and smaller subintervals. Do note again that this is identical to how we defined the real valued integral, so you can go back and connect this with how you learned that. One can argue similarly to how we defined our derivative formula that the integrals of vector functions can be spread out across their component functions. That's what this theorem says. So if r of t is equal to f of t times I plus g of t times j plus h of t times k, then the definite integral of r of t can just be computed as the definite integral of f times I plus the definite integral of g times j plus the definite integral of h times k. So just like we differentiated each component in order to find the derivative of the vector function, we can integrate each component in order to find the integral of the vector function. The fundamental theorem of calculus also applies to vector-valued functions, just like it does to real-valued functions. The first fundamental theorem of calculus says that if we let x, the upper bound of integration, be our variable, then the integral increases at a rate which is equal to the value of the function at x. That is, the derivative of the integral is equal to the value of the function at that endpoint. The version of the fundamental theorem of calculus that we use much more often is to actually evaluate integrals, which says that the integral from a to b of the function r is equal to an antiderivative of r at the endpoint b minus an antiderivative of r at the endpoint a. So let's solve a problem using an antiderivative here. Suppose that we're given that the derivative of a function, r prime of t, is equal to sine of ti plus t squared k. So this is probably a space curve. Suppose that we're also given the value of the vector function when t equals 0. It's negative 3, 5, 1. What's the value of the function when it's equal to pi? Well, notice that r needs to be an antiderivative of r prime. R of t and so what is r of t? Well, we can just take the antiderivative component-wise. So r of t equals, well, the antiderivative of sine is negative cosine t times I. The antiderivative of t squared is plus t cubed over 3k. But much like with single variable functions, we could add any constant vector to r of t, and its derivative would still be sine of ti plus t squared k. That's because the derivative of a constant function is 0. And so we're going to say plus c, but plus c is going to be a constant vector. That is, it has an I, j, and k component. In order to figure out what r of pi is, we're going to have to find out what r of c is. So the question is, what is c? Well, we'll use the information we have. We know r of 0. We know that negative 3, 5, 1 is equal to r of 0, which is negative cosine of negative cosine of 0i plus 0 cubed over 3k plus c. Well, that's equal to negative I plus c. And so we have negative 3i plus 5j plus k equals negative I plus c. We can now solve for c by adding I to the other side. C equals negative 2i plus 5j plus k. Now we know precisely what r of t is. Let's rewrite it. R of t equals negative cosine of ti plus t cubed over 3k minus 2i plus 5j plus k. We could, of course, collect like terms if we wanted to, but we're not going to need to in order to solve this problem. What are we asked for here? We're asked for r of pi. We have an expression for r of t, so let's just plug in pi. And we get r of pi equals negative cosine of pi times I plus pi cubed over 3k minus 2i plus 5j plus k. Negative cosine of pi is positive 1. Pi cubed is not something that we know how to simplify, so we should be able to write this as negative I plus 5j plus pi cubed over 3 plus 1k. And that is our answer.